thing about the DOM model, though, is DOM level 3 is a formal W3C standard. So all DOM parsers should at least theoretically act the same way. So an example of XML injection. Here we have an XML data item. It's got a username, an email, a password, a user ID, a group, and a password hint. Against a SAX parser, I could actually inject against this by simply, in my password hint, closing the hint tag and throwing in an additional value for one of the previous ones. For instance, I could throw in another UID and overwrite the previous one. Since the SAX parser is reading serially, later values will replace earlier ones. In a DOM parser, on the other hand, I might have to be a little more clever. In this case, I'm using an XML comment tag in one field I've injected into to comment out XML that's between that field and the next one. This way, when I go adding additional tags in my password hint, it doesn't have a collision with the previously assigned values. A DOM parser doesn't like XML that is not fully compliant. If you have the same value repeated more than once and the schema doesn't call for that, it won't parse it. So you have to be a little more clever to get past DOM parsers, and frequently to carry out an injection attack, you need to be able to inject into two fields. So attacking cloud storage applications. Amazon Web Services and Microsoft Windows Azure both use a wide variety of interfaces, but these interfaces are web services, and they are thus based on text strings. SimpleDB query strings are actually written in SQL. Azure Table Storage query strings aren't written in SQL, but it is a query language, which is roughly akin to what's in the where clause of a SQL statement. The Amazon Web Services SOAP API is XML-based. You're passing blocks of XML back and forth. And the Azure Blob Table and Queue Storage APIs are all XML. Even the requests are sent in XML, unless you're doing the simple URL-based blob storage retrieves. REST and SOAP interfaces are very popular for web services. While I'm just looking at Amazon and Azure in this talk, I imagine most other cloud database services, as those come into being, will probably use the same sorts of interfaces. I think we'll see these same problems with pretty much any app using cloud storage. Text strings are potentially subject to injection. So there are a variety of approaches we can take to try to attack an application that we know is using cloud storage. There's query string injection, where we attempt to modify the query string in a read. Direct node injection, where we try to inject XML straight into their XML API. DOM injection, doing the same thing. Persistent cross-site scripting. This isn't really an attack on the data layer, but I've seen applications trying to mitigate data attacks open themselves up to persistent cross-site scripting attacks. Storage enumeration is rather different from the rest of the things I'm talking about here, because it actually happens when you're trying to make files available to the public and have external users attached to your cloud storage directly rather than using it as a data backend. And finally, account level and infrastructure attacks. Since the database is sitting on the internet, if you don't properly protect the accounts in the database, it's possible for an attacker to actually directly connect to the database. The thing that's interesting here, all of these attack applications and users of cloud storage. Nothing I'm talking about today relies on any vulnerability or bug in either Amazon Web Services or Windows Azure. They, as far as I can tell, are implemented properly. Now, on the bright side, it's good that they've paid a lot of attention to security. Unfortunately, that means there's nothing to patch here. The things I'm talking about are things that developers are going to need to face as they move into cloud storage. So query string injection. Amazon Web Services SimpleDB uses SQL-like queries to query the tables. It's select attributes from domain, where conditions, with an order by and a limit optional clauses. The entire string is one parameter that gets sent to the REST API. So since this is one parameter sent to the API, things like the SDK aren't going to be doing anything with this parameter. You as the developer are responsible for assembling this parameter from strings and passing it into the API. The Azure Table Storage query string, as I've mentioned, is not SQL-like, but it is still one parameter, a string, encoded as a unit, and potentially subject to its own kind of injection attack. So since the query string is a single parameter, the onus is on the app developer to prevent injection. SimpleDB query strings support multiple quotation types and don't require escaping for one quotation type and closed in another. It's kind of like how PHP works, where if you want to put single quotes in a string, you can enclose the string in double quotes. The single quotes have no meaning in there, and they won't escape out of the string. An attacker who can control input to multiple fields thus can change the semantics of the query. So an example of how this could work. So here we have a simple query string. Select from products where category equals my category, intersection access equals public, order by column name. So in this case, I've got a set of products, some of which I display to everyone, some of which are private or access controlled in some way, and I'm letting the user sort and choose what category they're looking at. So I've got some access control mixed into here. This is not a good way to design an application. If I give malicious input with, say, some single quotes and double quotes in it, in this case, I've given an input of my category quote or category equals double quote and a sort order. Sort order would obviously not be typed in by the user, but sort order is often inserted by JavaScript when someone clicks a column header and sent back to the backend application. Well, if you're inserting with JavaScript, a user with an HTTP debugger can insert whatever they want there, and so they can insert arbitrary strings. Well, if I take that string and pass it back to the database as a query string, it's going to be interpreted this way instead. That's the same string with different highlighting. I'm now saying the category has to equal the one they selected, or the category has to equal a bunch of junk strings where I've just taken the access control out. And then I order by column name. So now I'm getting all data items rather than just the public ones. So the presence of multiple quotation types can allow users to insert or elide fields from the query. And the mitigation for this is identical to that for SQL injection. Validate user input, make sure there's not malicious input in it, and encode values before constructing a query string. The bad news here is there's no equivalent to parameterized queries. You as the developer have to construct the string. There's no way to have the API do that for you and avoid these sorts of problems. On the bright side, there aren't that many meta characters to encode here. Since you're sending data to the database backend, you're generally not worried about a lot of globalization and Unicode issues and so on. Though depending on your application, you potentially could be. The good news is that query strings only issue queries. You can't take one of these. In SQL, for instance, you could have or rather on a traditional SQL database, you could put in DDL, things like dropping a table, or putting in code to modify table schemas, to add users, and so on. There's no equivalent to that in these query strings. A query string in SimpleDB issues queries. It's a select query. You can't change reads to writes. You can't do other operations. All you can do is change what's being read. There's also no equivalent to CLR stored procedures, PL SQL, any of these other ways of executing code on the database. It's just reads. And since the verb is found outside of the query string, you can't do an insert or update or delete, because the way you do those with SimpleDB requires changing the REST call and not just changing the query string. So it's not as necessarily harmful an issue as a SQL injection in a relational database would be, but it's still something to consider. So XML injection. Windows Azure storage interfaces are XML sent over REST. And XML interfaces can also be subject to injection. It's less familiar than SQL injection. But here, since we're injecting directly into the API of the cloud storage provider, it is possible to do data writes and DDL-like operations. When I'm going through some of these examples, I'm not going to make assumptions about the SDK or API used. It's true that with Windows Azure Storage, most of the users of that are also using Windows Azure hosting, and thus they're writing in ASP.NET, and they're using Windows Communication Foundation. There's a lot of layers between them and the application. However, you can use Windows Azure Storage from any application. You can use it from a simple PHP application. It doesn't have to be hosted in Windows Azure. It could be hosted anywhere. So we can't make those assumptions about what kinds of interfaces are being used. The only way we can know what mitigations are in place is to try sending input to the program and seeing what happens. So here we have an attempt at a direct node injection. As I mentioned with SAX parsers, you can overwrite earlier values with later values. This was the first thing I tried, trying to attack a applications database layer. In this case, I'm going to use for an example on a lot of these a simple blog commenting and blogging application that I threw together in .NET. We have a title, a user ID, which is who posted it, an avatar URL, which is their user icon, and then the text of their comment. In this case, my user's comment text closes the comment text tag and then tries to overwrite user ID. That doesn't work. The parser's too sophisticated. The platform protects from this sort of attack. Even if I connect to the data endpoint directly and send this, it doesn't work. If you have duplicate nodes or any kind of schema validation errors, it invalidates the whole API call. You don't even get an error message. You get 400 bad requests with no other data provided at all. So this tells us we've got a DOM parser here. Thing about DOM parsers is DOM parsers are smart, and that makes them difficult to write. And as a result, they are generally very standardized implementations. Everybody uses the same few DOM parsers. So smart parsers usually implement the full XML specification. The fact that they implement most XML tags indicates they probably implement almost all of them. This includes things like XML comments and also block encoding with CDATA. CDATA is a special tag in XML which, once that tag opens, it tells it everything in the document until the CDATA closing tag should be considered a single blob of data. So no matter what XML meta characters are in that, carriage returns, binary data, and so on, it's all treated as a single unit and doesn't change the schema of the file. Everything until the closing tag, which is 2 right square brackets and a right angle bracket. So introducing these tags by an injection attack may allow modifying the XML. The advantage of these is we can change the meaning of the XML without introducing duplicate tags or messing up the XML structure. We're still going to have an XML file that is valid and parses without errors. Now, unfortunately for attackers, and fortunately for us, this actually has some drawbacks. It introduces junk into one or more tags. The problem with using XML comments and CDATA blocks is you don't have a way to get rid of those CDATA and comment opening and closing tags. So as a result, sometimes this stuff's going to be visible to users and so on, and not as hidden by the attacker as they might like. On the other hand, sometimes you can inject into fields that never display, and this actually isn't a problem at all. So here we have my same blog comment engine example, and in this case I've injected an XML comment. Assuming this is constructed from strings, if I can get an XML comment tag into my title, close it in comment text, I've elided some fields, and thus I can put in new replacement fields and not break the XML. It'll still parse correctly. In this case, what I've done with my new replacement fields is I've changed my user ID. So I'm now posting as a different user rather than as who I'm logged in as. I could do the same thing with a CDATA tag. In this case, I've got an opening CDATA tag in my title, and I close it in my comment text. The disadvantage there is this is a case where it's going to show to the user. That massive block of XML between the opening and closing CDATA, that just became the title of my blog comment, which is probably not, as the attacker, what I intended. However, with this particular XML structure, I don't have a choice if I have to use a CDATA tag to bring things out. I'm stuck with junk data in one of the tags. Those were demoed against Azure. There's no reason you couldn't do the same thing against SimpleDB. As you can see, this is a different XML schema. This is actually the contents of the SOAP envelope in a SimpleDB call. But it works the same way. The XML schema is different, but the principle is the same. So persistent cross-site scripting. When we're faced with these attacks against the XML data layer, people often turn to encoding to prevent XML attacks. So when I put in that XML comment or that CDATA tag, they get munged